Let's talk a bit more about the definite integral and how we might work to calculate some of these things, what their properties are going to be. Definite integral is a special kind of limit. We calculate a Riemann sum for a particular function, f of x. And what that looks like is we are measuring areas of rectangles. The height of each rectangle is taken from the value of the function itself. And the width of each rectangle is determined by how many rectangles we're using to fill up the interval, say, from A to B. Each one of these Riemann sums approximates the actual area between the graph of the function and the x-axis. And it's by taking the limit of those approximations as we let the number of rectangles in our approximation grow ever bigger, that limit will give us the actual amount of area. So, how much does this line up with my ideas about how areas should work? Here I have the graph of some function, and I've got my rectangles over here representing a Riemann sum. This looks to be a Riemann sum with n equals 8. There are 8 rectangles here. But this is only an approximation of the area that I can see in this picture. So what I would like to investigate is, how do I actually calculate these things? Let's run through an example. So let's calculate. And I want to take the integral. Let's start at an x value of 0, go up to an x value of 4. And I did say x, so this will be an integral by the variable x. So I'll have a dx on the end here. Very important that every integral has a dx or a dt or a dr or whatever our variable is going to be. And I need to tell you what function I'm interested in. So I will pick, let's just do a simple one. I'll have just integral of x dx. So this is saying that my function that I care about, f of x equals x. Now, the definition of this thing is I'm going to take the limit as n tends to infinity. And I need to look at the nth Riemann sum. So I start summation, I goes from 1 up to n. I have my f of xi. The heights of these rectangles will be different from each other, but I have my delta x. The widths of these rectangles are all the same parameter. Let's figure out what my heights will be. Let's figure out what my widths will be. Well, this interval starts at x coordinate 0, ends at x coordinate 4. So I know that this interval is 4 units wide. If I divide by n, that tells me that my delta x is the number 4 divided by n. So I'll get a slightly different width number depending on what n actually is. But this will be a useful formula when it comes time to calculate this limit. Now, if I'm going to make this calculation, I would like to know what my x values are going to be, right? What's my x sub I? I have some different choices. Let's go ahead and use right endpoints. So that if I think about this, here is my number line. I'm starting at 0. I'm going all the way up to 4. The first rectangle consists of all the x coordinates starting at 0 and going up to delta x. I can't type a delta, so I'll just draw this freehand. The second rectangle goes from delta x up to 2 times delta x. The third rectangle goes from 2 delta x up to 3 delta x, and so on. So if I want right endpoints, the right endpoint of the first rectangle is delta x. The right endpoint of the second interval is twice delta x. The right endpoint of the third rectangle is 3 times delta x. So that makes this a very handy thing to compute. I'm going to rewrite my limit formula. And now in the sum, I start at I equals 1, go up to n. But now I know what number xi is. Xi is the number I times delta x. So for the number 1 rectangle, I'm looking at delta x. For the number 2 rectangle, I'm looking at 2 times delta x, and so on. But even better than that, I actually know what my delta x is. Delta x is 4 divided by n. Now, my Riemann sum formula tells me I'm supposed to multiply by a delta x on the end here for the width of my rectangles. And I get this. Okay. Let me make a little bit more room here. Well, now that I know what my endpoints are, I'm going to figure out what is going on in this sum by evaluating this function. The function that I chose is easy enough. F of x is just equal to x. So this function has its output as just whatever number we put in as the input. So f of, let's call this I times 4 divided by n, or you might like 4i over n better. Well, if my input is 4i divided by n, then my output is also 4i divided by n. This particular function does not change the input in any way before it gives us the output back. Well, what can I do here? This sum is telling me to add up n numbers. The first of them will be 16 divided by n. The second of them will be 2 times 16 divided by, or excuse me, n squared. The second of them will be 2 times 16 divided by n squared. The third of them will be 3 times 16 divided by n squared, and so on. So I can actually factor things out of this sigma notation. So each of those sum n's has a 16 in it. Each of them has an n squared in the denominator. And now what I'm really adding up are all of the whole numbers, starting at 1, finishing at n. Well, I know how to do that calculation, actually. So in the limit, n goes to infinity. So far, I've just been doing algebraic work here. I haven't calculated the limit just yet. Well, I've got that 16 divided by n squared that I factored out of each of the summands. And then the formula for adding up the first n integers, I can calculate that by n times n plus 1, all divided by 2. Okay. Then I can cancel a little bit. I can cancel an n from the denominator and an n from the numerator. I can cancel a factor of 2 off of that 16 and the 2 from the denominator. This looks to be 8 times n plus 1, all divided by n. Now in the limit, as n goes to infinity, this fraction right here is going to go to 1. How do I know that? Well, I could rewrite it slightly. Nobody ever got hurt from multiplying by 1. So I can just multiply numerator and denominator by 1 divided by n. And that should help show that this limit is the same as the limit of 1 plus 1 over n, all divided by 1, times 8, of course. So this limit is going to be 8. Now, if I think about this, what kind of region do I have here? If I start at 0, go up to 4, the function that I've got is just y equals x. Well, that's just a line. What amount of area do I have here? I've got the area of a triangle whose width is 4 units and whose height is also 4 units. So how much area does such a triangle have? Width times height divided by 2, that's going to be 8. So yes, I did get exactly the amount of area that I thought I should get. So it's nice to test these things out with functions whose area I can predict, just to make sure that I'm on the right track. But now I could change this function. Instead, look at the integral of x squared. So most of my work here would be the same, except for right here, I would have 4i over n all squared times 4 over n. So this wouldn't be 16 over n squared. I'd have something slightly different. I would have (64) divided by n cubed. And then I wouldn't be adding up the first n whole numbers. I'd be adding up the first n perfect squares. And then, the rest of the work, I'd have to redo basically everything else that comes after. I'd need a different formula for adding up all the squares. Now, ultimately, I want to be able to do these calculations without having the clever formula for adding up a whole bunch of integers, adding up a whole bunch of squares, and so on. But the key thing to remember is that all of this really does come down to this area concept. So I have some function, I have some area between the graph of that function and the x-axis, with the technicality that area above the x-axis will count positively and area below the x-axis will count negatively. This was a consequence of the choice of our approximation, right? If we take all the heights from the function itself, what do we do with negative heights? Well, That would mean subtracting area. Now, this area idea lets me better understand some of the properties that the integral will have. So on this slide here, and again on the next couple slides, are some of the properties about the definite integral. And they're all written out using the algebraic notation here. But all of these things are properties that we would expect to see from working just with geometry and measuring areas of certain shapes. So this first one, if a and b are the same number, then the integral is automatically equal to 0. Why should that be? If my starting point for the integration and my stopping point for the integration are the same, well, then I've just got a line segment. Line segments don't have, line segments don't have area. So that actually makes sense from the geometry point of view. This second one is a little bit of a technicality, right? So if I integrate from b up to a instead, if I go backwards, then all that does is put an extra minus sign outside the integral. Well, why should that happen? The reason for this one has to do with my formula for the delta x. If delta x is b minus a all divided by n, and I switch the order of a and b, then I've changed my delta x from being a positive number to a negative number. So this comes up as a consequence, again, of just following that formula for approximating the area. This third one looks a little bit complicated. The integral from a to b of the constant function that just produces c for all values of x, dx, is equal to c times the quantity b minus a. And again, c is any constant. Well, that seems like a lot, but this is just the way to describe the area of a rectangle. If your height is c the whole way through, and you start at a and you stop at b, our width is the quantity b minus a, and areas of rectangles are simple. They're just the product of the height times the width. In fact, that was the whole thing that got us started out down this path. If we are told to integrate the sum of two different functions, then we can integrate one of the functions and then add to that the integral of the other. Why is that? Well, in this picture down here, I can see that I've got two functions, f and g. And the function f plus g, I've just lifted each of my rectangles up to sit on top of the function g of x. So I should be able to count up these areas separately and then just add them back together after I know what they are. And similarly for number 5 here, if I stretch my function along the y-axis, right? If I stretch it up vertically, if I compress it vertically, I do that by multiplying by a constant. But if I think about what those rectangles in the Riemann sum would be doing, each of those rectangles would be stretched or shrunk by that same constant multiple. So I can get the same calculation by looking at the constant c times the integral. So kind of like with derivatives, actually, we can add functions and do the integrals of those things separately. We can multiply a constant onto the function, but we can just factor that outside of the integral. That's not so bad. And we can even go one step further, and we can say that if we are integrating the difference of two functions, that's the same calculation, or at least the same result as the integral of one of the functions minus the integral of the other one. Now, integrals tell us where to start and stop counting area. That's the whole point of the integration sign. The lower endpoint is where we start. The upper endpoint is where we stop. So if we integrate starting at A and stop prematurely, and then start up again and keep going until we hit B, then the total amount of area here should be equal to the blue area plus the dark gray area, which is saying that I can add together two different integrals as long as they are integrals of the same function, and as long as the upper endpoint of one of the integrals matches the lower endpoint of the other of them. So we can split up integrals in this way, and then we can recombine them as long as their formulas match in that way. It sounds complicated, but really it's just saying that I can slice up area how I like. Area on the left should be some kind of integral. Area on the right should be some kind of integral. And it doesn't matter if I take area in two different places and then combine those numbers that I got, or if I integrated it all at once. That's really what this rule is saying. Here's a couple more. If I know that my function is never a negative number, if my f of x is greater than or equal to 0, then of course my integral, my amount of area, must be greater than or equal to 0. The only way I get negatives showing up in here is if I've got rectangles of negative height, which means that my function f of x had to go below the x-axis. Makes sense. Well, I can do a little bit better than that. If my function f of x is always greater than or equal to some other function g of x, then the integral of f has to be more area than the integral of g. Now, for some reason, this is shown in the opposite way in this picture down here. The curve on top is g of x, the curve on bottom is f of x, but I can just see from the picture, I'm expecting the amount of area covered by the g of x function is more than the area covered by the f of x function. And it just comes down to geometry. Now, this is a handy thing because if my function is always bound between two different numbers, say that lowercase m is a lower bound on the function f, uppercase m is an upper bound on the function f, then my integral itself is going to be bound between these two different areas. What area is this? This area is the area of the rectangle underneath my function, using lowercase m as the height, b minus a as the width, and then over here I've got the larger rectangle, which has to be more area. Let's keep going. Number 11 is a version of the triangle inequality. right? If we take the absolute value of the sum of two different numbers, that will be less than or equal to the sum of the absolute values of those two numbers. And it works for integrals as well. Again, because I don't know if my rectangles are representing positive area or negative area. So if I integrate the absolute value of a function, I'll get a bigger integral than taking the absolute value after doing the integration. So that seems like a lot. This is the last one that I would like to talk about for today. And that is if my function f is a continuous function, well then I know, first of all, I've got some amount of area here covered by my curve. I can just build up a rectangle who has the same height as, has a height that gives me an area equal to that of the integral. And because my function f does not have any jumps, it doesn't have any discontinuities here, then my function f of x actually has to cross this rectangle somewhere. So this is a really special one because this is almost saying that for a continuous function, we could have found the exact area with one single rectangle in our Riemann sum. Now, this isn't quite as practical as we might hope. The trick is in finding that particular value of C that would make this formula work. But it's still interesting from a theoretical perspective that there would be at least one place on the graph of this function where a single rectangle Riemann sum exactly matches the amount of area here, the amount of area represented by the integral. Okay, that's been kind of a lot. So you might want to rewind and go through those a second time. It's kind of a lot to chew on. I like to think of it that these are just slightly different ways of writing out some geometrical ideas that I can split up areas and calculate them separately, that I can tell when one area is going to be bigger than another just by which of these has the larger y coordinate. So I'll end here for today, and I'll see you again soon.